Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Light had always been humanity's companion and tool, but for millennia it remained fundamentally uncontrolled in its nature. The sun scattered its energy across the sky, flames flickered in unpredictable patterns, and even the most carefully designed lanterns produced illumination that spread in all directions, weakening with distance according to immutable physical law. Every photon traveled independently, waves of electromagnetic radiation propagating outward from their source without coordination or coherence. This was the natural state of light, chaotic, dispersed, diminishing rapidly as it moved through space. The limitations became apparent whenever precision was required. A surgeon needed to see clearly into the tiny spaces where instruments worked, but brighter lights meant more heat and more illumination of surrounding tissue that only obscured the target. A manufacturer cutting metal could use mechanical saws that generated tremendous friction and heat, wearing down over time and limiting the complexity of possible cuts. A scientist measuring distances needed to account for the spread of light beams, which widened and weakened as they traveled, making precise measurements over long distances nearly impossible. The tools available for working with light were all bound by the same constraint. Light naturally diverged, spreading its energy across ever larger areas. Communication over distances faced similar limitations. Flags and mirrors could send signals that eyes could interpret, but only across spans where the human eye could still distinguish shapes and flashes. Electrical signals through wires allowed communication over continental distances, but they required physical connections and infrastructure that took years to install and maintain. Radio waves could travel without wires, but they spread in all directions, requiring powerful transmitters and sensitive receivers, and the amount of information they could carry was limited by the frequencies available and the interference from other transmitters sharing the electromagnetic spectrum. Industrial processes that required concentrated energy faced fundamental constraints. Welding metal demanded heat intense enough to melt steel, achieved through electric arcs or burning gases that were difficult to control precisely. Cutting required mechanical force applied through edges that dulled and broke. Engraving meant physically removing material through contact, limiting the fineness of detail that could be achieved. Every process that required energy to be focused into a small area struggled against the physics of how energy naturally dispersed. Heat dissipated through conduction and radiation. Mechanical forces distributed across contact areas. Light spread according to its wavelength and the imperfections in any lens or mirror trying to focus it. The dream that began to form in the minds of physicists and engineers was simple in concept, but profound in implications. What if light could be made coherent, with all its waves synchronized and traveling in the same direction? What if photons could be induced to emit in phase with each other, building rather than interfering? What if a beam could be created that didn't spread appreciably even over vast distances, maintaining its intensity and focus? The need wasn't yet clearly articulated because the possibility seemed so remote. But across various fields, people were encountering the same fundamental limitation: that energy, and particularly light, naturally dispersed rather than concentrated, and that this constraint limited what could be achieved. The problem of measurement at a distance became particularly acute as technology advanced and precision requirements increased. Surveyors needed to establish exact positions across miles of terrain, but their instruments relied on light or mechanical means that accumulated errors over distance. The electromagnetic waves they used spread into cones rather than traveling as narrow beams, limiting accuracy. A beam of light sent across a valley would arrive at its destination, having widened by meters or more, making it impossible to establish position more precisely than that spread allowed. The surveying community could compensate through repeated measurements and statistical analysis, but the fundamental limitation remained. Their light sources were incoherent. Medical procedures struggled against the imprecision of existing tools. A scalpel, no matter how sharp, had a blade of finite width and cut through mechanical pressure that disturbed surrounding tissue. Cauterizing blood vessels required heat that affected areas beyond the immediate target. Removing unwanted tissue meant cutting it away, inevitably damaging adjacent healthy tissue in the process. The human body contains structures measured in fractions of millimeters, nerves, blood vessels, cellular layers that required intervention at scales finer than mechanical tools could easily achieve. Light was known to carry energy, but conventional light sources were too diffuse to be useful for such precise work. The emerging field of data transmission and storage faced limitations imposed by the physical properties of the media being used. Electrical signals through copper wires traveled at high speeds, but were subject to interference and degradation over distance. The wires themselves were expensive to manufacture and install, and the amount of information they could carry was limited by their electrical properties. Radio transmission required no wires, but faced similar bandwidth constraints and was subject to interference from weather, geography, and other transmissions. The amount of information modern society needed to transmit was growing faster than the capacity of existing transmission methods, creating pressure for new approaches that could carry more data in the same physical space. Manufacturing processes that could create increasingly complex products needed better tools for precision work. Electronics were becoming smaller, requiring the ability to create features measured in thousandths of inches. Traditional machining methods using cutting tools couldn't achieve the precision needed. Chemical etching could create fine patterns, but was messy, dangerous, and limited in the materials it could process. There was growing recognition that being able to direct energy precisely to very small points would enable manufacturing techniques that weren't currently possible. The energy needed to be controllable, predictable, and capable of being turned on and off rapidly. Light seemed like an ideal candidate because it carried substantial energy and could theoretically be focused very tightly. But existing light sources were too incoherent to be useful. Research itself faced limitations in studying the fundamental nature of matter and energy. Physicists needed to probe atomic and molecular structures to understand how matter absorbed and emitted light, to explore the quantum behaviors that govern the universe at small scales. Their experiments required light sources with specific properties, single wavelengths, precise timing, known polarization. Natural light sources and most artificial ones produced mixtures of wavelengths and incoherent emissions that made precise experiments difficult. The tools needed for advancing understanding of physics didn't yet exist, creating a circular problem where the knowledge needed to create better instruments required experiments that couldn't be performed without those instruments. The theoretical foundations emerged from quantum mechanics, that peculiar description of reality at atomic scales where particles behaved like waves and waves behaved like particles. Physicists had discovered that atoms could exist only in specific energy states, not in the continuous range of energies that classical physics would predict. When an atom absorbed energy, perhaps from collision with another particle or by absorbing a photon of light, it jumped to a higher energy state. When it returned to a lower state, it emitted the excess energy as a photon with a frequency determined precisely by the energy difference between the states. This explained the spectral lines that had puzzled scientists for decades. Why heated elements emitted light only at specific wavelengths rather than across a continuous spectrum. The crucial insight came from considering what happened when atoms already in excited states encountered photons that matched the energy difference between their current state and a lower one. Normally, excited atoms decayed spontaneously, emitting photons in random directions at random times. But the theory predicted that a photon passing near an excited atom could trigger it to emit an additional photon identical to the triggering one. Same wavelength, same direction, same phase. This stimulated emission contrasted with the spontaneous emission that occurred naturally. If conditions could be created where stimulated emission dominated over absorption and spontaneous emission, a single photon could trigger emission of many identical photons, creating an amplification effect. The concept required specific conditions that seemed difficult to achieve. The material containing the atoms needed to have more atoms in excited states than in lower states, a population inversion that was the opposite of thermal equilibrium, where lower energy states were always more populated. This inversion needed to be maintained while photons passed through the material, triggering emissions that produced more photons. Some mechanism needed to keep photons traveling back and forth through the material multiple times to maximize amplification. And the whole system needed to preferentially emit photons in a single direction with coherent phases rather than scattering them randomly. Early theoretical work suggested that microwaves might be easier to work with than visible light because their longer wavelengths corresponded to smaller energy transitions that were easier to produce in atoms or molecules. Researchers began exploring ways to create population inversions in gases, using molecular energy states that could be separated by external electric or magnetic fields. The first successful devices operated in the microwave region of the electromagnetic spectrum, producing coherent electromagnetic radiation at wavelengths measured in centimeters rather than the fractions of a micrometer characteristic of visible light. These devices proved the principle. Stimulated emission could indeed produce coherent, amplified radiation. The extension to visible light seemed logical, but presented significant challenges. The energy differences between atomic states that produced visible photons were larger, requiring more energy to create population inversions. The shorter wavelengths demanded much more precise optical elements to contain and direct the light. Materials needed to be found that could maintain population inversions despite the high photon densities that visible light involved. The gain medium, the material where amplification occurred, needed optical quality without impurities or irregularities that would scatter light. The mirrors that would reflect light back and forth through the gain medium needed to be parallel to within fractions of a wavelength across their entire surface. The engineering challenges were substantial, but the theoretical framework suggested that success was possible if the technical problems could be solved. The optical cavity became a central concept in designs for visible light devices. Two highly reflective mirrors placed parallel to each other would trap light between them, forcing photons to pass repeatedly through the gain medium where population inversion existed. On each pass, stimulated emission would amplify the light, with photons triggering additional emissions that added to the beam. Most of the light would reflect back and forth, building in intensity, but one mirror would be made partially transparent, allowing a small fraction of the light to escape as the output beam. The cavity would preferentially amplify only those wavelengths that fit exactly between the mirrors, waves that completed an integer number of cycles in traveling from one mirror to the other and back. The geometry of the mirrors determined the properties of the output beam. Flat mirrors would create unstable cavities where small misalignments caused light to walk off the mirrors rather than being trapped. Curved mirrors could create stable configurations where light naturally stayed confined even with minor imperfections in alignment. The spacing between mirrors needed to be carefully controlled because changes of even a wavelength would shift which frequencies were amplified. Temperature changes that expanded or contracted the cavity length by microscopic amounts would affect operation. The entire assembly needed to be rigid and isolated from vibration to maintain the precise alignment and spacing the physics required. Population inversion could be achieved through various methods, each with advantages and disadvantages. Optical pumping used intense light from external sources to excite atoms in the gain medium to higher energy states. The pumping light needed to be absorbed efficiently by the gain medium, while the laser light being produced needed to be emitted freely without reabsorption. This required careful selection of materials with appropriate energy level structures. Electrical discharge through gases could create inversions through electron collisions that pumped energy into atoms. Chemical reactions could produce excited molecules that then emitted coherent light as they relaxed. Each approach required different engineering solutions and produced different operating characteristics. The threshold condition determined whether a device would work at all. The amplification from stimulated emission needed to exceed all the losses, from absorption in the gain medium, from scattering at imperfections, from transmission through mirrors, from diffraction at edges. Below threshold, light would amplify slightly, but would die away after multiple passes through the cavity. Above threshold, amplification would exceed losses, and light would build up rapidly to limited by saturation effects. The threshold depended on material properties, cavity design, pumping intensity, and dozens of other factors that needed to be optimized simultaneously. Early researchers struggled to achieve lacing because they didn't yet understand all the loss mechanisms that were preventing their devices from reaching threshold. The coherence properties that would make these devices useful depended on the physics of stimulated emission. Unlike spontaneous emission, where photons emerged with random phases, stimulated emission produced photons with phases locked to the triggering photon. As the light built up in the cavity through repeated passes, the coherence improved because photons out of phase with the dominant mode didn't experience as much amplification and were suppressed. The result would be light, with all its waves in phase, traveling in the same direction, with a very narrow distribution of wavelengths. This coherence was what would make the light so different from any previous source: focused, intense, and capable of being manipulated in ways that incoherent light couldn't achieve. The first successful visible light devices emerged from laboratories after months or years of incremental progress punctuated by moments of unexpected success. Researchers experimented with different gain materials: synthetic ruby crystals doped with chromium atoms that would provide the necessary energy levels, gases containing carefully chosen mixtures of elements, semiconductor materials where electron-hole recombination could produce photons. Each material required its own pumping mechanism and cavity design. The ruby devices used intense flash lamps wrapped around the crystal rod, flooding it with light that excited the chromium atoms. The optical quality of the crystals needed to be exceptional. Any strains or impurities would scatter the laser light and prevent threshold from being reached. The first beams that emerged were revelations to those who witnessed them. A bright red spot appeared on a distant wall with an intensity that seemed impossible from such a small device. The beam didn't spread noticeably even across the length of the laboratory. When directed at materials, the concentrated energy could burn paper, pop balloons, and heat metals in ways that no previous light source had achieved. The coherence was evident in the way the light behaved. It could be focused to spots smaller than any conventional light source. Interference patterns showed waves aligned with precision that exceeded measurement capability. The success proved that the theoretical predictions were correct and that practical devices could indeed be built. Gas-filled tubes offered an alternative approach where electrical discharge through the gas created the population inversion. The gases needed to be chosen for their energy level structures and excited by high voltage electricity passing between electrodes. The gain was lower than solid-state materials, but the devices could operate continuously rather than in pulses. The tubes were fragile, glass envelopes that needed to maintain precise pressure of gas mixtures while containing electrodes and optical windows. The mirrors were mounted externally, allowing adjustment but requiring incredible stability to maintain alignment as temperatures changed and vibrations disturbed the system. Early versions required constant tweaking to keep them operating. Semiconductor devices represented a third approach that would eventually dominate many applications. At the junction between differently doped semiconductor materials, electrons and holes could recombine to produce photons. If the current was high enough, population inversion could be achieved and the junction could serve as a gain medium. The mirrors could be formed by cleaving the semiconductor crystal along natural crystal planes that acted as partial reflectors. The resulting devices were tiny, smaller than grains of rice, and could be powered by modest electrical currents. But they initially required cooling to cryogenic temperatures to operate because thermal vibrations at room temperature disrupted the population inversion. Power levels increased as understanding improved and engineering refined the designs. Early devices produced milliwatts of output, enough to see easily, but not enough for most practical applications. Improvements in materials quality, better mirror coatings that reflected more light while losing less, more efficient pumping mechanisms, and thermal management to remove heat that limited performance all contributed to steady increases in power. Pulse devices could produce enormous peak powers by storing energy and releasing it in very short bursts. The pulses lasted millions or even billions of seconds, but during those brief intervals, the power could exceed that of entire power stations, all concentrated into a beam narrower than a pencil. The wavelengths available expanded as researchers discovered more materials with suitable properties. The ruby devices produced red light, but applications would need other colors. Gases could produce various wavelengths depending on their constituents. Helium and neon together produced red light, but other gas mixtures produced infrared or even ultraviolet. Dye lasers used organic molecules dissolved in liquids, and by choosing different dyes or adjusting their concentrations, the output wavelength could be tuned across wide ranges of the spectrum. The diversity of wavelengths meant that applications could choose light with properties optimized for their specific needs. Wavelengths that materials absorbed strongly for cutting, or that transmitted through tissue for medical procedures. Stability became a focus as devices moved from demonstration curiosities to tools that needed to perform reliably. Temperature fluctuations caused cavities to expand and contract, shifting the wavelength and intensity of output. Mechanical vibrations disturbed mirror alignment, causing the beam to wander or even extinguish entirely. Contamination of optical surfaces from dust or degradation of coatings reduced output over time. Manufacturers developed environmental controls, temperature stabilization, vibration isolation, sealed cavities to keep contaminants away from optics. The devices became more complex, but also more reliable, able to operate for hours or days without intervention, rather than requiring constant adjustment. Modulation techniques allowed the light to carry information by varying its intensity, frequency, or phase in patterns that could be decoded at a receiver. The coherent nature of the light meant that very small changes could be imposed and detected, enabling transmission of enormous amounts of data through a single beam. The narrow beam width meant that transmissions could be directional rather than broadcast, improving security and reducing interference. Fiber optic cables could guide the light over distances of miles while maintaining signal quality that would have degraded hopelessly in copper wires carrying electrical signals. The implications for communications were recognized even before the technical challenges of implementation were fully understood. Medical researchers began exploring applications cautiously, aware that the concentrated energy could cause damage as easily as provide benefits. The ability to deliver energy precisely to small volumes of tissue opened possibilities that didn't exist with conventional surgical tools. Wavelengths could be chosen that were absorbed by specific tissues. Blood vessels absorb differently than surrounding tissue. Pigmented lesions absorb differently than normal skin. By selecting appropriate wavelengths and pulse durations, targeted tissue could be heated and destroyed while leaving adjacent areas unharmed. The precision was remarkable compared to scalpels that cut through everything in their path. But the novelty meant that techniques needed to be developed carefully through research before clinical application. Industrial applications emerged as power levels increased to where materials could be processed. The focused beam could deliver enough energy to melt or vaporize metals, creating cuts without mechanical force or tool wear. The cuts were narrow, the width of the beam itself measured in fractions of millimeters. Complex shapes could be created by moving the beam or the workpiece under computer control. Materials that were difficult to machine conventionally because they were too hard or brittle could be processed by light that didn't care about mechanical properties. Welding became possible by precisely controlling the energy delivered to create molten zones that joined materials. The non-contact nature meant that delicate parts could be processed without mechanical stress. The gain medium required careful preparation to achieve the optical quality and material properties that the physics demanded. In solid-state devices, crystals needed to be grown with extreme purity, introducing dopant atoms in precise concentrations while excluding contaminants that would absorb or scatter light. The growth process took weeks, with molten materials slowly crystallizing under controlled temperature gradients in furnaces that maintain conditions within narrow tolerances. Even microscopic variations in dopant concentration would create regions where amplification differed, producing output beams with irregular intensity profiles or preventing threshold from being reached at all. The polishing of crystal ends that would serve as surfaces for light to pass through demanded extraordinary precision. The surfaces needed to be flat to within fractions of a wavelength across their entire area. Deviations of a few hundred nanometers would introduce aberrations that scattered light and reduced efficiency. The polishing process involved progressively finer abrasives, with final stages using compounds that removed material atom by atom until the desired surface quality emerged. Inspection required interferometric measurements that revealed surface topology through the interference patterns created when test beams reflected from the surface. Any scratches or pits, even microscopic ones, needed to be polished away because they would create localized heating when the intense beam passed through. Mirror fabrication evolved into specialized art as the demands on reflectivity increased. Early devices used simple metallic coatings that reflected perhaps 90% of incident light, but 10% loss per bounce meant that light made only a few passes through the cavity before being absorbed or scattered away. Advanced mirrors used multi-layer dielectric coatings, alternating layers of materials with different refractive indices, each layer having a thickness of a quarter wavelength. The interference between reflections from each layer interface created constructive interference for the desired wavelength, achieving reflectivity exceeding 99.9%. The coating process required vacuum deposition equipment that could control layer thickness to nanometer precision across the entire mirror surface. The mechanical mounts that held optical elements needed to provide both rigidity and adjustability. Mirrors mounted in the mounts required alignment to ensure they were parallel and perpendicular to the optical axis, with adjustment mechanisms allowing fine positioning measured in microradians. But once aligned, the mounts needed to hold position despite temperature changes, mechanical vibrations, and acoustic disturbances. The materials of construction needed low thermal expansion coefficients and high stiffness. Invar alloys, ceramics, and specialized metal composites found use because they maintain dimensional stability better than common materials. Kinematic mounts used contact geometries that prevented over-constrained conditions where thermal stress could cause misalignment. Cooling systems became essential as power levels increased and the heat generated by inefficient conversion of pump energy to beam energy needed removal. The gain medium absorbed pump light that didn't contribute to population inversion, converting it to heat that raised temperature and could even crack crystals if not controlled. Cooling channels machined into holders or jackets around gain media circulated chilled water or other coolants. The coolant temperature needed stabilization because temperature changes altered the refractive index of materials, affecting cavity length and beam quality. High-power devices used sophisticated thermal management with multiple cooling loops, heat exchangers, and temperature sensors feeding back to control systems that maintained operating points. The pump sources evolved from crude to sophisticated as efficiency and reliability requirements increased. Early flash lamps were essentially large photographic flash units, producing intense bursts of broadband light by discharging electrical energy through xenon gas. The lamps aged rapidly. Each flash degraded the electrodes slightly, and after thousands or tens of thousands of pulses, the lamps needed replacement. The spectrum of light they produced was broad, with much of the energy at wavelengths the gain medium didn't absorb, wasting pump energy as heat. Continuous arc lamps provided steady illumination, but generated tremendous heat that needed to be removed from both the lamp and the gain medium it illuminated. Semiconductor pump sources represented a significant advance, producing light at wavelengths that could be precisely matched to absorption peaks in the gain material. The diode pump devices were more efficient because most of the pump light was absorbed usefully rather than being converted to waste heat. The diodes themselves were small, allowing arrays of them to be packaged tightly around the gain medium or coupled through fiber optics to deliver pump light precisely where needed. They lasted for thousands of hours of continuous operation rather than thousands of pulses, reducing maintenance requirements. The electrical drivers needed to provide constant current through the diodes while protecting them from voltage spikes or thermal overload that would damage the semiconductor junctions. Beam delivery systems transported light from the source to the point of use, requiring optical elements that could handle the intensity without damage. Mirrors needed coatings resistant to the laser wavelength, with damage thresholds exceeding the peak intensity the beam would deliver. Lenses focused beams to small spots where energy concentration was highest, making them vulnerable to damage from dust particles or coating defects that absorbed energy and created hotspots. The focusing optics needed materials transparent at the operating wavelength. Common glass absorbed ultraviolet and infrared wavelengths, requiring specialized materials like fused silica, calcium fluoride, or zinc selenide, depending on the specific wavelength. Articulated arms with mirrors at each joint allowed beams to be directed flexibly for industrial applications like cutting and welding. The mirrors needed to maintain alignment despite the mechanical motion of the arm, requiring precise manufacturing and assembly. Protective windows prevented debris generated during processing from contaminating the optics, but the windows themselves absorbed some energy and needed cooling or periodic replacement. Fiber optic delivery offered an alternative where light coupled into the end of a flexible fiber could be transported distances of meters with minimal loss, emerging from the other end to be focused onto the workpiece. The fiber cores needed to be large enough that power density didn't damage the material, and the end faces required careful preparation to prevent back reflections that could destabilize the source. Safety systems protected operators from exposure to beams that could damage eyes or skin in fractions of a second. Mechanical shutters blocked beams when not in use, controlled by interlocks that prevented opening until safety conditions were verified. Enclosures around work areas captured reflected and scattered light, with access doors that automatically shut down the source when opened. Warning lights and signs indicated when devices were energized. Protective eyewear filtered the wavelength being used while transmitting other wavelengths so operators could see their work. The mechanical aspects of safety required attention to failure modes. Shutters needed to fail closed, interlocks needed to be tamper-resistant, and enclosures needed to withstand accidental beam impacts without developing holes that would allow light to escape. The classification of devices by hazard level emerged as essential for establishing appropriate safety protocols across diverse applications. The classification scheme considered output power, wavelength, beam divergence, and exposure duration to assign devices to categories representing different risk levels. The lowest category included devices so low in power that they couldn't cause harm even with direct eye exposure, common in consumer electronics where beams might be visible. Higher categories represented progressively greater hazards, with the highest reserved for devices capable of causing instant eye damage or skin burns from direct or reflected exposure. Each category required specific control measures, from simple warning labels to engineered enclosures and safety training. Wavelength-specific standards addressed the particular hazards associated with different regions of the electromagnetic spectrum. Ultraviolet wavelengths posed risks to cornea and lens that were different from infrared, which penetrated deeper into tissue. Visible wavelengths created blink reflexes that provided some protection for brief exposures, while invisible wavelengths allowed extended exposure before pain or damage provided warning. The standards specified maximum permissible exposure levels that varied with wavelength, exposure duration, and tissue type, providing quantitative limits that system designers and safety officers could apply to determine if adequate protection existed. Interlock requirements standardized how devices would prevent operation under unsafe conditions. The standards specified that interlocks needed to be fail-safe, designed so that failures resulted in safe conditions rather than allowing hazardous operation. Interlocks on protective enclosure doors needed to cut power when doors opened, with redundant switches preventing single-point failures. Defeat mechanisms that might allow bypassing interlocks for maintenance required key control and administrative procedures to prevent casual circumvention. The mechanical design of interlocks used positive actuation, physical contact that opens circuits rather than proximity, sensing that might fail without indication. Beam delivery standards addressed safe practices for systems that directed output to workpieces or patients. The standards required that beam paths be enclosed or located in controlled areas where only authorized personnel had access. Mirrors and lenses in the beam path needed to be secured so they couldn't be accidentally misaligned to direct beams toward people. Beam stops captured light that missed its intended target or continued beyond it. The standards prohibited common materials like shiny metal surfaces near beam paths because specular reflections could create secondary hazards difficult to predict or control. For surgical applications, standards required backup aiming beams, pedal switches to give surgeons control without removing hands from the surgical field, and systems that limited exposure duration. Maintenance and inspection protocols became standardized to ensure devices remained safe throughout their operational lifetime. The protocols specified periodic measurements of output power, beam quality, and pointing stability to verify that devices operated within their design parameters. Safety systems required functional testing, verifying that interlocks actually prevented operation, that shutters closed completely, that warning indicators functioned properly. Documentation requirements created paper trails showing that inspections occurred and that any deficiencies were corrected before devices returned to service. Calibration of instruments used for these tests needed traceable standards to ensure measurements were accurate and comparable across different facilities. Medical application standards address the unique challenges of using concentrated light on human tissue where effects needed to be therapeutic rather than harmful. The standards required extensive preclinical testing to establish safe parameters for each combination of wavelength, pulse duration, power density, and tissue type. Treatment protocols needed documentation showing that they achieved intended effects without excessive collateral damage. Training standards specified that operators needed detailed knowledge of tissue optics, wound healing, and potential complications specific to the procedures they would perform. Informed consent documents needed to explain risks in language patients could understand. Manufacturing standards for medical devices established design controls ensuring that devices performed consistently and safely. The standards required risk analysis during design to identify potential failure modes and verify that controls existed to prevent or mitigate them. Design validation needed to demonstrate that devices met specifications across the range of conditions they would encounter in clinical practice. Manufacturing process controls ensured that each device was built identically to validated designs. Post-market surveillance systems tracked adverse events to detect problems that might not have been apparent during development, feeding information back to improve future designs. Industrial safety standards addressed hazards beyond the beam itself that arose during materials processing. Cutting and welding produce fumes containing vaporized material, metal oxides, and combustion products that required ventilation systems to protect operators from inhalation exposure. The bright light from the interaction zone could damage eyes through intense visible and ultraviolet radiation, even without direct beam exposure, requiring appropriate screening. Fire hazards existed because focused beams could ignite flammable materials, requiring fire suppression systems and protocols for identifying and removing combustibles from work areas. Noise from high-power devices and associated cooling systems needed attention to prevent hearing damage. Electrical safety standards applied because high-power devices required substantial electrical infrastructure, often including high-voltage power supplies that presented shock and arc flash hazards. The standards specified grounding requirements, insulation ratings, and overcurrent protection appropriate for the power levels involved. Access to electrical components required interlocks or administrative controls, preventing contact during operation. Stored energy in capacitor banks or other components needed to be discharged and locked out before maintenance. The standards required that electrical hazards be clearly marked and that personnel working on devices had appropriate training and used proper procedures and personal protective equipment. Environmental standards addressed disposal of materials containing hazardous components and management of wastes generated during operation. Some devices contain toxic materials in their construction: beryllium in mirrors, lead in solder, rare earth elements in crystals. Standards specified proper handling during manufacture, use, and end-of-life disposal. Chemical wastes from cooling systems or cleaning processes required management according to their hazard classification. Energy efficiency standards emerged as power consumption became a concern, encouraging designs that minimized waste heat and electrical consumption. The standards created framework ensuring that the benefits of the technology didn't come at unacceptable environmental cost. The incorporation into consumer electronics happened so gradually that most people never consciously noted the change. The small semiconductor devices that could fit inside portable music players and laptop computers served as reading mechanisms for optical discs, focusing tiny spots of light onto reflective surfaces encoded with patterns of pits that represented digital information. The precision required to track spirals of data with spacing measured in micrometers, all while the disk spun at thousands of rotations per minute, demonstrated how far the technology had progressed from laboratory curiosities to reliable components produced by millions. The devices were sealed inside equipment, invisible to users who simply inserted discs and expected them to work. Barcode scanners at checkout counters replaced manual price entry, the scanning beam reading patterns of lines that encoded product information. The scanners needed to read codes regardless of orientation or distance within certain ranges, requiring sophisticated optics and signal processing. Multiple scanning beams at different angles created patterns that would intersect barcodes however items were presented. The technology worked so reliably that it became invisible. Customers and cashiers alike took for granted that passing items over scanners would instantly identify them and their prices. The mechanical sound of early scanners gave way to nearly silent operation as rotating mirrors were replaced by solid-state scanning mechanisms. Printers in homes and offices used scanning beams to create images on photosensitive drums, which then attracted toner particles that transferred to paper. The precision of the system allowed printing of text and graphics at resolutions exceeding what the human eye could distinguish, with registration accuracy requiring positioning within micrometers. The speed of printing increased as scanning mechanisms and processing improved, with pages emerging at rates of dozens per minute. The technology became so common that the engineering sophistication hidden inside every printer went unnoticed. The precise timing of multiple subsystems, the optical quality of lenses and mirrors, the thermal management of the fusing system that melted toner onto paper. Fiber optic communication systems carrying phone calls, internet traffic, and television signals relied on transmitters that converted electrical signals into pulses of light, which then traveled through hair-thin glass fibers, spanning continents and crossing oceans. The transmission rates increased from millions to billions to trillions of bits per second as technology advanced, with each fiber carrying the equivalent of thousands of simultaneous phone conversations or hundreds of high-definition video streams. Repeater stations periodically amplified signals that had weakened over distance, using specialized designs that added energy directly to the optical signals without converting them to electrical form and back. The global communications network came to depend on these systems, without most users understanding that light pulses were carrying their data. Entertainment venues incorporated scanning systems that created patterns of colored beams, moving in time with music to create visual spectacles. The beams could write images in the air, using the persistence of human vision, with points of light moving so quickly that eyes perceived continuous lines and shapes. Atmospheric effects from fog or haze made the beams themselves visible as they swept through space. The shows required precise synchronization between music, beam position, color, and intensity, all controlled by computers running programs choreographed to create specific emotional effects. The technology that had seemed exotic became a routine part of concerts and celebrations, its ubiquity making it unremarkable even as the technical achievement behind it remained considerable. Manufacturing processes integrated the technology so thoroughly that products people use daily had been touched by focused light at some point in their creation. Circuit boards inside electronics had holes drilled by beams that could create thousands of precisely positioned openings per minute without toolware or the need for drilling pilot holes. The positioning accuracy allowed dense packing of components, enabling miniaturization of devices that fit in pockets and weighed mere ounces. Markings on products, serial numbers, dates, logos, were engraved by removing thin layers of material with pulses timed to microseconds, creating permanent marks that wouldn't wear away like printed labels. Automotive manufacturing embraced welding applications where beams joined body panels and structural components, with strength exceeding traditional spot welding while leaving minimal visible marks. The precision allowed welding in areas inaccessible to conventional tools, creating new possibilities for vehicle design. The speed of welding enabled production rates matching the overall pace of assembly lines, with robotic systems positioning parts and initiating welds under computer control. The investment required for the systems was substantial, but the improvements in quality and reduction in weight of finished vehicles justified the expense for manufacturers producing millions of units. Medical procedures expanded beyond early experimental applications to become standard treatments for conditions that previously required more invasive surgery or had no effective treatment at all. Eye surgery to correct vision involved reshaping the cornea by removing microscopic amounts of tissue, guided by precise measurements of each patient's optical imperfections. The procedure took minutes, with healing measured in days rather than weeks, and outcomes that often eliminated the need for corrective lenses. Removal of kidney stones used pulsed beams to fragment the stones into pieces small enough to pass naturally, avoiding surgical incisions. Treatment of certain cancers involved heating tumors with light delivered through thin fibers, killing abnormal cells while sparing surrounding healthy tissue. Quality inspection systems used scanning to measure dimensions, detect defects, and verify assembly of manufactured products. The non-contact nature meant delicate parts could be inspected without damage, and the speed allowed every part to be checked rather than relying on sampling. Three-dimensional scanning captured surface geometry by measuring reflections from multiple angles, creating digital models accurate to micrometers that could be compared to design specifications. Surface finish could be assessed by analyzing how light scattered from textures too fine for human vision to evaluate. The automation of inspection improved quality while reducing costs, making precision manufacturing economical for products that would have been too expensive to produce with manual inspection. Research laboratories across disciplines incorporated the technology into instruments that had become essential for scientific investigation. Spectroscopy systems used tunable sources to probe how materials absorbed and emitted light at specific wavelengths, revealing information about chemical composition and molecular structure. Microscopy techniques used focused beams to image biological samples at resolutions beyond what conventional microscopes achieved, sometimes using non-linear effects that only occurred at high intensities to generate contrast. Particle manipulation systems used radiation pressure to trap and move microscopic objects, enabling experiments that studied individual molecules and cells. The tool that had emerged from physics research had become instrument-enabling research across biology, chemistry, materials science, and numerous other fields. The manufacturing facilities that produced devices at commercial scale represented significant capital investments, with clean rooms maintaining environmental conditions that prevented contamination during fabrication. The air inside these rooms passed through filters that removed particles larger than fractions of a micrometer, creating environments cleaner than hospital operating rooms. Temperature and humidity remained constant within narrow tolerances because variations would affect the dimensional stability of equipment and the properties of materials being processed. Personnel entering clean rooms wore specialized garments that covered hair and skin, preventing human-shed particles from contaminating work surfaces or products. Crystal growth furnaces occupied entire rooms, with thermal insulation surrounding chambers where materials melted at temperatures exceeding 1,000 degrees. The process of growing a single crystal could take weeks, with computer control systems maintaining temperature gradients while slowly withdrawing a seed crystal from the molten material. The resulting crystal ball would be several inches in diameter and a foot or more in length, representing the starting point for dozens of finished devices. Any power interruption or control system failure during growth would ruin the ball, making reliable electrical infrastructure and backup systems essential for facilities where each successful growth represented substantial value. Coating equipment for producing multi-layer dielectric mirrors required vacuum chambers large enough to hold multiple mirrors while maintaining pressures 1 billion times lower than atmospheric. The chambers were constructed from stainless steel with precision machined sealing surfaces using elastomer gaskets that could withstand repeated cycling between atmospheric pressure and high vacuum. Pumping systems used multiple stages, mechanical pumps to remove most of the air, then turbomolecular or cryogenic pumps to reach the final vacuum level. Inside the evacuated chamber, electron beams or ion guns vaporized coating materials, which then condensed on mirror substrates, rotating to ensure uniform thickness. Testing facilities needed to measure device performance across multiple parameters, requiring specialized instrumentation that was itself often sophisticated and expensive. Power meters measured output using thermal or photodiode sensors calibrated against national standards, with uncertainties typically less than a few percent. Beam profilers captured two-dimensional intensity distributions, revealing whether devices produced the expected beam quality or had aberrations indicating problems with optical elements or alignment. Spectral analysis equipment measured wavelength distributions with resolution fine enough to detect mode structures and verify single frequency operation where required. The capital cost of test equipment could rival the cost of production equipment. But without accurate measurement, there was no way to verify that products met specifications. Supply chains for components and materials stretched globally, with specialized suppliers providing items that devices required, but that manufacturers didn't produce themselves. Optical glasses and crystals came from companies with expertise in materials, science, and crystal growth. Precision mechanical components were machined by shops with equipment capable of holding tolerances measured in micrometers. Electronic control systems incorporated components from semiconductor manufacturers, power supply specialists, and companies producing sensors and actuators. The complexity meant that disruption at any supplier could affect production, creating vulnerability to events ranging from natural disasters to geopolitical conflicts that affected international trade. Service and repair networks developed to support the installed base of devices operating in facilities worldwide. Preventive maintenance schedules specified periodic cleaning of optics, replacement of consumable components like flash lamps or pump diodes, and recalibration of control systems. The service needed to be performed by personnel trained in the specific models being maintained, with access to proprietary information about adjustment procedures and diagnostic techniques. Some manufacturers operated their own service organizations, while others licensed independent service companies to perform maintenance. The economic model shifted partially from equipment sales to ongoing service contracts, creating recurring revenue streams that helped manufacturers through periods when new equipment sales declined. Spare parts inventories needed to be maintained because failures could idle expensive production equipment or disable critical medical systems. But the diversity of models in the field, each potentially requiring different components, made comprehensive spare parts stocking economically challenging. Critical components that were likely to fail or wear out, optical elements, pump sources, cooling system components, needed to be available locally or regionally to minimize downtime. Electronic modules could often be shipped overnight, but mechanical assemblies that required precision machining might have lead times of weeks, if not kept in stock. The balance between inventory, carrying costs, and the costs of equipment downtime required careful analysis. Training infrastructure emerged to provide the specialized knowledge that operators and maintenance personnel required. Manufacturers offered courses at their facilities where customers could send employees for hands-on training with equipment identical to what they would encounter in their workplaces. Online training provided basic information and refresher courses that could be accessed without travel. Certification programs verified that individuals had achieved competency in specific procedures, with periodic recertification ensuring skills remained current as technology evolved. Universities and technical colleges added curriculum covering the theory and practice of working with concentrated light, preparing students for careers in industries that depended on the technology. Regulatory infrastructure varied by application and jurisdiction, but generally required that devices meet safety standards before being sold and that facilities using them comply with regulations protecting workers and the public. Medical devices required approval demonstrating safety and efficacy through clinical trials before they could be marketed. Industrial systems needed to comply with occupational safety regulations and, in some cases, obtain operating permits. The regulatory agencies employed inspectors who visited facilities, reviewed documentation, and verified compliance. The burden of regulatory compliance added costs and time to bringing new products to market, but provided assurance that minimum standards were met. Research infrastructure at universities, national laboratories, and corporate research centers continued exploring physics and engineering challenges that would enable future capabilities. The research required facilities with specialized capabilities, ultra-high vacuum systems for studying fundamental light-matter interactions, high-speed measurement equipment for characterizing pulses lasting femtoseconds, clean rooms for fabricating experimental devices incorporating new materials or designs. Funding for this research came from government agencies supporting basic science, from industry partners interested in specific applications, and from internal investments by companies seeking competitive advantages. The time between fundamental research breakthroughs and commercial products could span decades, requiring sustained commitment to support work whose payoff was uncertain and distant. The diffusion of technology across borders happened through multiple channels, each contributing to the global spread of capabilities that had initially been concentrated in a few advanced industrial nations. Scientific publications shared theoretical insights and experimental results, allowing researchers worldwide to learn from each other's successes and failures. International conferences brought together practitioners from different countries, facilitating informal exchange of knowledge and establishing personal relationships that enabled future collaboration. Graduate students from developing countries studied in advanced programs abroad, then returned home bringing expertise that helped establish domestic capabilities. Export controls complicated the free flow of technology for systems considered to have military applications or strategic value. Governments restricted what could be sold to certain countries or what technical information could be shared with foreign nationals, even those working at domestic institutions. The controls created friction in international scientific collaboration and business relationships, requiring export licenses for equipment and careful review of technical papers to ensure they didn't disclose controlled information. The effectiveness of these controls was debatable. The fundamental physics was published openly, and determined nations could eventually develop indigenous capabilities even without access to foreign technology, though perhaps more slowly and at greater cost. Manufacturing capabilities spread to new regions as companies sought lower production costs or access to growing markets. Facilities established in countries with lower labor costs could produce devices economically for price-sensitive markets, even if they initially assembled components manufactured elsewhere. Over time, local supply chains developed, with domestic companies learning to produce components that had previously been imported. Government policies in industrializing nations often encourage this technology transfer through requirements that foreign companies partner with domestic firms or establish local production facilities as conditions for market access. Medical applications spread unevenly, with adoption fastest in wealthy countries where healthcare systems could afford capital-intensive equipment and where regulatory systems had processes for evaluating new treatments. Developing countries often gained access to the technology later, sometimes through donations of used equipment from wealthier nations upgrading to newer models. Medical tourism emerged where patients traveled internationally to receive treatments not available or more expensive in their home countries, creating economic incentives for some nations to invest in advanced medical capabilities that would attract foreign patients. Industrial adoption followed similar patterns, with early users in advanced economies gradually joined by manufacturers in developing countries as both equipment costs decreased and the economic advantages of precision manufacturing became apparent. The technology enabled manufacturing of products with complexity and quality that would have been difficult or impossible with conventional methods, allowing countries to compete in global markets for high-value goods. The patterns of adoption reflected broader industrialization trends, with textile and consumer electronics manufacturers in certain regions adopting the technology extensively, while other sectors or regions lagged behind. Standards. Bodies with international membership work to harmonize technical specifications and safety requirements across national boundaries, facilitating trade in equipment and allowing workers trained in one country to operate systems safely in another. The standards addressed everything from electrical connectors and mounting dimensions to measurement methods and terminology. Achieving consensus required negotiation among delegates representing different national interests, technical perspectives, and economic stakes. The resulting standards were often compromises that no participant found perfect, but that all could accept as reasonable baseline requirements. Intellectual property considerations affected how technology spread internationally. Patents granted companies exclusive rights to practice inventions in countries where the patents were filed, creating temporary monopolies that allowed recovery of research and development costs. But enforcing patents internationally was challenging, especially in countries where legal systems provided limited protection or where enforcement was inconsistent. Companies needed to balance protecting innovations through patents against maintaining trade secrets that never became public. Some chose to patent extensively and license technology to others, while others kept key innovations secret and relied on manufacturing expertise that was difficult to replicate. Collaborative research projects involving institutions from multiple countries pooled resources and expertise to address challenges beyond what any single organization could tackle alone. These collaborations required navigating differences in research cultures, funding cycles, and administrative procedures across participating institutions. Language barriers sometimes complicated communication, though English served as lingua franca for most technical discussions. Intellectual property agreements needed to specify how discoveries would be owned and how commercial benefits would be shared. Negotiations that could be contentious when participants had different priorities or valued contributions differently. Market dynamics created interesting patterns where companies from different countries specialized in different aspects of the technology ecosystem. Some nations developed strengths in crystal growth and optical materials, while others excelled in precision manufacturing of mechanical systems or semiconductor fabrication. The specialization reflected historical accidents, government policies, and the accumulation of expertise and infrastructure over time. The result was global supply chains, where finished products incorporated components from multiple countries, each contributing elements where they had competitive advantages. Cultural factors influenced adoption patterns in ways that went beyond economic or technical considerations. Safety culture varied between regions, affecting how willingly organizations adopted technologies with inherent hazards. Regulatory approaches ranged from prescriptive rules specifying exact requirements to performance-based standards, allowing flexibility in how safety was achieved. Legal systems that were more or less litigious affected how aggressively companies marketed applications with any potential for harm. Medical treatment preferences varied culturally, with some societies more willing to adopt new technological approaches, while others preferred established treatments, even when new options offered advantages. The question of whether the technology represented progress or merely change prompted debates that had no clear resolution. Proponents pointed to concrete benefits, medical procedures that were less invasive with faster recovery, manufacturing processes that produced better products with less waste, communication systems that connected humanity more thoroughly than ever before. Critics noted that each application brought new risks and that the march of technology seemed to accelerate without adequate consideration of long-term consequences. The concentrated energy that enabled beneficial applications could also cause harm if misused or if safety systems failed. The dependency on complex technological systems created vulnerability to disruptions that would have been unthinkable in simpler times. The accessibility question became pressing as applications matured and proliferated. Medical treatments using the technology were often expensive, raising equity concerns about whether they would be available only to wealthy individuals or societies. Industrial applications required capital investments that favored large manufacturers over small ones, potentially accelerating consolidation. The knowledge required to design, build, and maintain systems created demand for highly trained specialists. But educational systems in many regions lacked capacity to produce enough graduates. Without conscious effort toward equitable access, the benefits could accrue primarily to those already privileged, while others were left behind. The environmental considerations involved complex trade-offs that resisted simple evaluation. Manufacturing the devices required energy-intensive processes and materials extraction with environmental footprints. But applications often replaced more wasteful processes. Cutting with light used less energy than mechanical methods in some cases. Fiber optic communications used less energy than copper wire systems carrying equivalent data. Longer device lifetimes and higher efficiency reduced resource consumption over product life cycles. Enabling precision manufacturing could reduce material waste. But the rapid pace of technological advancement meant devices often became obsolete before wearing out, creating electronic waste streams requiring proper management to prevent environmental contamination. The dual-use nature of the technology created ethical dilemmas for researchers and developers. The same devices that enabled surgery could be weaponized to blind or burn. Communications capabilities enhanced civilian life, but also enabled military applications. The range-finding and target designation systems in weapons incorporated technology identical in principle to surveying instruments and autonomous vehicles. Researchers faced choices about whether to work on applications with potential military use, whether to publish results that might inform weapons development, and how to respond when their work was used for purposes they found objectionable. There were no universal answers, only individual decisions made according to personal values. The question of human obsolescence arose as automation advanced and systems took over tasks previously requiring human skill and judgment. Industrial workers who had spent years developing expertise in welding or cutting or machining watched as automated systems replaced them, producing results as good or better with less labor. Surgeons wondered whether their most precise work would eventually be delegated to robotic systems guided by computer vision. The pattern was familiar from previous technological transitions, but the pace seemed faster and the range of affected occupations broader. Society needed mechanisms to help displaced workers transition to new roles, but the political will to create and fund such mechanisms often lagged behind the technological change creating the need. The aesthetic appreciation of coherent light emerged among those who worked closely with it, finding beauty in properties that seemed almost unnatural compared to ordinary illumination. The perfect collimation of beams that traveled without spreading, maintaining tight focus across vast distances, appeared almost like solid rods of light rather than the diffuse glow of conventional sources. The monochromatic purity, with all photons sharing nearly identical wavelengths, created colors of unusual saturation and intensity. The speckle patterns that appeared when coherent light reflected from rough surfaces showed intricate granularity that shifted and changed with the slightest movement, revealing the interference of waves in ways invisible with ordinary light. The philosophical implications of coherence itself invited reflection on order and randomness. Ordinary light sources produced photons independently, with random phases that interfered destructively as often as constructively, the waves cancelling each other as much as reinforcing. Coherent emission produced waves marching in lockstep, their phases synchronized so they reinforced to create intensities exceeding what any number of independent emitters could achieve. This represented a kind of order imposed on nature, where quantum mechanics and carefully engineered systems conspired to produce behavior wildly different from equilibrium. The devices were entropy-decreasing machines, concentrating energy and imposing order in defiance of thermodynamic tendencies toward disorder. The question of whether focused light represented a fundamentally new tool or merely an extension of existing capabilities divided observers. Some argued it was qualitatively different, that the ability to deliver energy with precision and control that previous tools couldn't match created possibilities truly unlike what had existed before. Others countered that it was quantitatively better, but not qualitatively novel, doing faster or more precisely things that mechanical and thermal processes already accomplished. The debate was partly semantic, turning on definitions of fundamental versus incremental innovation. But it touched on deeper questions about how to recognize genuinely new capabilities versus improvements on established approaches. The role of serendipity in technological development appeared clearly in the history of coherent light, where practical applications often emerged unexpectedly long after theoretical foundations were established. The initial theoretical predictions came from physicists exploring fundamental quantum mechanics, not engineers seeking new tools. The first successful devices were built to prove concepts, not to solve practical problems. Applications emerged as people with problems encountered the technology and recognized potential connections. This pattern, fundamental research without clear application, eventually enabling technologies that transformed industries, provided argument for supporting basic science, even when immediate utility wasn't apparent. But the long timescales between discovery and application tested the patience of funding agencies and political systems. The ownership of knowledge and technology raised questions about whether fundamental discoveries and their practical implementations should be considered common heritage or private property. Patents granted temporary monopolies on inventions, justified as necessary incentives for innovation, but criticized as impeding follow-on research and limiting access. Academic researchers debated whether accepting industry funding compromised their independence and whether discoveries made with public funding should be freely accessible rather than patented. The tension between private incentive and public benefit appeared repeatedly, with different societies making different choices about how to balance them. No consensus emerged about optimal policy, only ongoing negotiation among stakeholders with competing interests. The trajectory of power scaling pointed toward capabilities that would have seemed impossible when devices first emerged from laboratories decades earlier. Developments in materials science promised gain media with higher efficiency and better thermal properties, allowing extraction of more energy per unit volume without the thermal management challenges that limited current systems. Novel pumping architectures using fiber-coupled diode arrays could deliver pump light with unprecedented uniformity and efficiency. Advanced cooling systems using microchannel heat exchangers and phase change materials would remove waste heat more effectively, enabling continuous operation at power levels currently achievable only in pulses. Ultra-short pulse generation continued advancing toward ever briefer durations, with pulses lasting femtoseconds or even attoseconds, time intervals so short that light traveled distances comparable to atomic dimensions during a single pulse. These pulses contained enormous peak powers despite modest average energy, because all the power was concentrated into such brief intervals. The applications for these extreme pulses included studying chemical reactions as they occurred, watching electrons move in atoms, and processing materials with such precise energy delivery that surrounding material remained completely unaffected. The physics at these timescales revealed behaviors invisible at longer durations, opening new regimes for both fundamental research and applied technology. Wavelength expansion into regions of the spectrum, not yet well served by existing technology, remained an active research area. The far ultraviolet and extreme ultraviolet wavelengths, with photons energetic enough to ionize atoms, enabled lithography for semiconductor manufacturing with feature sizes measured in nanometers. The terahertz region between microwave and infrared offered capabilities for security scanning and communications that were just beginning to be explored. X-ray wavelengths remain challenging because materials absorbed rather than reflected them, making conventional optical cavities impossible. But developments in free electron sources suggested routes to coherent X-rays that could image individual molecules. Beam shaping capabilities were advancing beyond simple focusing to create complex intensity distributions tailored for specific applications. Spatial light modulators using arrays of tiny mirrors or liquid crystal elements could impose arbitrary patterns on beams, creating multiple focal points simultaneously or structured beams with intensity distributions optimized for particular material processing or medical procedures. Adaptive optics borrowed from astronomy could correct for distortions in optical systems or in media through which beams passed, maintaining beam quality through atmospheric turbulence or biological tissue. The ability to sculpt light in space and time promised applications that current simple focused beams couldn't address. Integration with other technologies would likely accelerate, with coherent light systems becoming components in larger systems rather than standalone tools. Additive manufacturing systems were already using scan beams to selectively melt powder into three-dimensional objects, but future systems might incorporate sensing and feedback to adjust processing in real time based on measured properties. Autonomous vehicles might use ranging systems that sent out pulses and measured time of flight to build detailed three-dimensional maps of surroundings. Quantum computers might use trapped atoms manipulated by carefully controlled beams to perform calculations impossible on conventional computers. The boundaries between disciplines would blur as the technology enabled new capabilities at their intersections. The biological applications remained largely unexplored compared to what the underlying physics might eventually enable. Optogenetics, which used light to control genetically modified neurons, was revealing how brain circuits functioned and might eventually allow treatment of neurological conditions. Light-based sensing of biological molecules could enable diagnostic tests that were faster, more sensitive, and less invasive than current approaches. Photodynamic therapy, where light-activated drugs that had been introduced into the body offered ways to treat cancers and infections with spatial precision that systemic drug administration couldn't achieve. The gentle interaction possible with low-intensity beams could manipulate individual cells without damage, enabling assembly of engineered tissues. The question of accessibility would likely intensify as capabilities increased and costs potentially decreased through manufacturing improvements and economies of scale. Would the benefits reach populations currently lacking access, or would disparities widen? The trajectory could go either direction, depending on conscious choices about technology development and distribution. Open-source designs for simpler systems might enable local manufacturing in resource-limited settings. International aid programs might subsidize equipment for developing regions, or market forces alone might concentrate advanced capabilities in wealthy societies, while others may do with older technology. The outcome would reflect values and priorities as much as technical possibilities. The educational challenges of preparing future generations to work with increasingly sophisticated systems required rethinking traditional curricula. The knowledge base spanned quantum mechanics, optics, electronics, materials science, computer control, and application-specific domains like medicine or manufacturing. No individual could master all these areas deeply, requiring collaborative teams with diverse expertise. Educational systems needed to prepare students both for specialization in particular aspects and for working across disciplinary boundaries. The pace of technological change meant that education needed to emphasize fundamental principles and learning skills rather than specific technical details that might become obsolete within careers spanning decades. The philosophical journey from curiosity-driven research to ubiquitous technology offered lessons about how human knowledge and capability evolved. The theoretical foundations emerged from physicists asking abstract questions about light and matter, with no thought of practical application. Decades passed before laboratory demonstrations proved the concepts could be realized physically. More decades elapsed before engineering development produced reliable devices. Applications emerged gradually as people recognized connections between capabilities and needs. The entire process spanned generations, requiring sustained support through long periods where progress was uncertain and benefits remained speculative. The light itself remained unchanged throughout this journey. Photons obeying the same quantum mechanical laws they always had, traveling at the constant speed imposed by the structure of space-time, interacting with matter according to selection rules determined by atomic structure. What changed was human understanding and the ability to create conditions where light's inherent properties could be harnessed for purposes nature never intended. The devices were asking nature to do what it could do, but normally didn't, to produce coherent rather than random emission, to build up intensity through repeated amplification, to maintain phase relationships across macroscopic distances. The technology represented not violation of natural law, but deep understanding of what nature permitted, coupled with engineering skill to create conditions where permitted behaviors actually occurred. The story of concentrated light was ultimately a story of human curiosity, persistence, and ingenuity, gradually revealing and then utilizing possibilities that had always existed but remained hidden until inquiry illuminated them. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.